Okay, so if you remember it, on our Monday lecture, we started looking at what we mean by a scattering cross-section. Eventually, we will be aiming at calculating these cross-sections. We first started with the classical definition. We said that, okay, so if you have a scattering center, the cross-section is basically what is the small area that you should target in the perpendicular plane, such that if you hit that area, the particle will scatter in some direction. So this is the classical definition. And then we generalize this classical definition to basically this is what we had obtained, is a particle flux into the detector times the area of detector gives us the number of particles reaching my detector per second, divided by the particle flux into the target, how many particles do we send into the target. So this ratio is something that gives us the cross-section, even in the classical limit. So this definition actually matches the other definition in the classical case. And the advantage of this definition is that this is also applicable in the quantum case. You see, in quantum, even if you treat your system quantum mechanically, you can always measure the particles, number of particles arriving in your detector. You can always measure the how many particles that you are sending into your scattering center. So these quantities are measurable quantities. So we can use this definition also in the quantum mechanical sense. So we don't need to aim our particle at a given area, but it's enough to calculate how many of them scatter in towards my detector. So this will also give me the probability of scattering into the detector. So this will be proportional to, let's say, the probability that the particles that I send will move in the direction of my detector after the scattering. So now we kind of express this scattering cross-section in terms of probabilities, which we can calculate in quantum mechanics. Okay, so any questions about this cross-section? That is what we will be targeting at. So we will ask ourselves the question, let's say that we send a particle with a given momentum towards the scattering center. So what is the probability that it will, after a sufficiently long time, what is the probability that I will be measuring that particle to be moving in a given direction? That is the question now I will ask. And this time we will be doing so-called time-dependent perturbation theory. So what I will be assuming is I'm creating some particles at some early time, then let my system evolve, and I will measure the state of my system at a later time. So you see, when we were doing the time-independent perturbation theory case, you were kind of all confused that which happens first and something happens. We always talked about, okay, there's the first interaction with the potential, the second interaction with the potential, but I was insisting that there's no time there. There is no first, there is no last. Now in this definition, it will be more obvious, at least now we will have some time. So we have, initially I have a state that I create at t is equal to, at the time minus t, I let it evolve to a later time, and then ask myself the question, what is the amplitude that at that evolved state will be in some momentum eigenvalence state? So that is basically this matrix element, this overlap amplitude over there. So this is how we usually define the S matrix. You have some initial state, some final state. Your initial state is at the time minus t, final state is at the time plus t. So you evolve it by 2t and eventually take the limit as t goes to infinity. So that is the problem that we are trying to address. How can we calculate this matrix element? And to simplify the computation, we introduce a third picture. You should already be familiar with the Schrödinger picture, in which the states are evolving in time, the operators are time independent. Then there is a Heisenberg picture where the states are time independent. Whatever state you create, that stays as it is, but the operators are time dependent. And the third picture that we introduced, so-called interaction picture, is somewhat in between, because now our Hamiltonian, we kind of separate it into two parts. One is H0, which we can solve. The other one is V, which we cannot solve. So we let the operators evolve under H0. So that evolution we know, because we can solve H0. And then there is the V, the states evolve under V. And then, okay, we define our states in the interaction picture. We asked ourselves the question, how does the interaction picture state change with time? You say, this is how the interaction picture state changes in time. We have introduced that operator U, which we define in this form. You say H in the Schrodinger picture gives us the full evolution of the state, full time evolution of the state. Some of that time evolution is due to H0, and we essentially subtract that, cancel that. You say this factor cancels the evolution due to H0 only. So the time evolution of the state in the interaction picture is given by this equation here, where U is our evolution operator in the interaction picture. Then we asked ourselves the question, what are the properties of U? Rather than trying to calculate this directly, we said, okay, so let's first look at its derivative. We already know the initial value. At t is equal to t0, it should be 1, because both of those exponents are 1 separately. Let's see what its time derivative is. And when we calculate the time derivative, okay, it's here. Here we have the time derivative of U. Well, the time derivative of U is just V times U. Of course, now V is not the time-independent V, but the V in the interaction picture. Since in the interaction picture, operators are evolving only due to H0, in principle, we know what Vi is. We know V, so we can calculate Vi. So this is just looks like a very simple first-order differential equation with the given boundary condition. Now, of course, since these are if these were not operators, the U just would turn out to be the exponent of V. But since they are operators, things get a bit complicated, but still we managed to convert it to a form. This is where we had left. So we said that U, the time evolution of the state, is determined by this operator U, which is the time-ordered exponential of minus I times Vi of t integrated from t0 to t. Of course, this is the formal solution, so we know what our state is. Well, calculating or making computation with this solution would not be so trivial. That is what we will be doing more or less today. So any questions up to here? So let's continue. This was our U. Time-ordered exponent. Do you remember the definition of the time-ordered exponent? Well, the interaction picture operators depend on time. If you have the product of more than one operator, well, let me write this first. If you have two operators, operator 1 at time t1, operator 2 at time t2, this will be equal to operator t1 times operator t2 if t2 is earlier, operator t2 times operator t1 if t1 is earlier. Whichever operator is earlier, we move it to the right. So now you can actually see that eventually we will calculate in perturbative expansion. We will have the products of VIs. They will be time ordered. So one operator will act before the other operator. So just if you remember what we had done in the time-independent perturbation theory case, now all the things that we said, okay, this acts before, the other one acts after, it will be valid. We will see that. Because now we have time dependence in this picture, and things act before or after. Now, another thing I would like you to keep in mind that we will be working with plane waves. Well, plane waves are kind of pathological. You cannot normalize them to one. They are spread out everywhere. So you cannot create even localized packages. They are not localized packages. So when I say that I create a plane wave over here and send it towards the scattering center, it's not strictly speaking correct, because if I say that there is a plane wave, well, it's not over here, it's everywhere. Some of it is over here, some of it is over here, some of it is over there. It's everywhere. So you can ask, okay, if the plane wave is so spread out, does it have any physical significance? Well, you can also make exactly the same derivations with localized packages. They will not be exactly plane waves, they will not be exact eigenstates of the momentum, but I mean, the size of that packages will be determined by the uncertainty in your measurements. But if you consider for a particle that has a, let's say, a large enough momentum with a small enough uncertainty in momentum, the uncertainty in the position will be at this, a reasonable uncertainty, let's say, consistent with our experimental measuring devices. The localization, the uncertainty in position is at the atomic size. You see, if we could say that its momentum is definitely this without any error bars, the uncertainty in position should be infinite, but for all practical purposes, for reasonable uncertainties in momentum, the size of the uncertainty in position will be of the size of an atom or a large molecule. So I can still talk, I mean, if you ever read experimental papers or experimental work, they will talk about particles having a given momentum being at a given point. It's not against the uncertainty principle, but the limit of the uncertainty principle is really, for most practical cases at least, it's not really relevant. I can consider a very localized wave function in momentum space, which will still be very localized in coordinate space compared to, let's say, the atomic size. And when I will be talking about, let's say, oh, I send a particle from minus infinity. Well, minus infinity can be just 100 atomic sizes. That's all. That's very far away. So for human standards, well, I can just do this formalism I can use to describe process happening on this tabletop. Infinitely long, infinite far away would be this point from the center for all fundamental processes. For example, if you consider the lifetime of the neutron, do you remember the lifetime of neutron?
11 minutes.
Around 10-15 minutes. Well, that is infinitely long for all practical purposes. Most electromagnetic processes happen at the order of 10 to the power minus 8 seconds or so. So if you are looking at electromagnetic processes, anything of the order of 10 to the power minus 8 or larger is infinitely long. So whenever we are saying, okay, I will be dealing with plane waves still, I won't do the wave package picture. But in Peskin and Schroeder, there is a nice discussion about these wave packages. He starts with wave packages, assumes that he creates wave packages at some place over here, sends them, calculates their evolution. I would advise you to at least go over it. The final result doesn't really change.
Sorry, stupid question, and I'm not trying to be rude, but like, have we said anything that we don't already know from free particles in regular non-relativistic quantum mechanics?
No.
Right? No, okay. It's the same.
Not even, I mean, this description is valid in non-relativistic mechanics or relativistic mechanics.
Right.
I didn't even say it's non-relativistic. The only thing I said is that I have a Hamiltonian. It can be a relativistic Hamiltonian, non-relativistic Hamiltonian. It can be, in the non-relativistic case, p squared over 2m, or it can be the Hamiltonian I wrote in terms of my fields. In fact, if you remember our time-independent perturbation theory case, we just considered that an interaction potential which we wrote in terms of our fields. So this V, whenever you see this V over here, you can also remember that same V, because essentially we will be driving the same result, but with a formally more intuitive means, let's say. And there's also, I mean, you'll probably be bored of hearing the same thing and over again. In field theory, we are doing quantum mechanics. Here, this is just a quantum mechanical description of whatever potential you have. As long as you can separate your Hamiltonian into two parts, one part you can solve, the other part you cannot solve exactly, so this formalism will be valid. And for those who took 508, this will be just a boring repetition of the same things we did in class. But that is just you.
Yeah. Second stupid question, why didn't mathematicians just invent quantum field theory? Why not just quantize?
Why should they?
Why do they do anything? Like, why not? Like, I mean, seems like a natural generalization. Right? You have.
Yeah, you see, there are all kinds of infinities that will appear, which mathematicians don't like.
Okay. But there's no historical program where they tried for no reason?
Well, you see, who invented field theory? I would say, if I would pick one name, I would say Dirac. He was the first one to quantize electromagnetism. Well, is he a physicist or a mathematician? The boundary is kind of blurred.
He's an electrical engineer. Okay.
Anyway, so the boundary is kind of blurred. Well, you see, when you start with physics, you start with the physicists, they usually start with a physical motivation. Now you have a problem that you need to solve. Mathematicians, they don't have this constraint, let's say. For example, group theory, they invented it without any use in physics, first of all.
That's why I'm surprised that they didn't do this.
Well, I'm not even sure if they didn't do it. I mean, sometimes they just do it and
no one knows.
No one knows. Until a physicist comes out and tries to apply it to physical processes.
Yes.
Anyway, let's continue along this line. So this is my wave function at the time t in the interaction picture is time-ordered exponential minus I t0 up to t vi of t prime dt prime psi of t0. Now, what does this mean? This will be 1 minus I from t0 to t plus minus I squared from t0 to t dt1 t0 to t1 dt2 vi of t1 acting on our state psi t0. Okay, when I said in our last lecture that we didn't really achieve much, we just found a short way of writing this infinite sum. This is what I meant. If you want to make some computation with this time-ordered exponential, we have to again expand it anyway. But now let's go back to our problem. What I'm interested in, I will be sending t0 up to minus infinity. There's no problem with that. I will keep t as t. But if I send t0 to minus infinity, some of the integrals become problematic because, you see, the integrals might not converge. So I would replace my v as v times e to power eta t. And eventually take the limit eta goes to 0. So basically what I'm assuming is at t is equal to minus infinity, there is no interactions. Well, in the package description, it doesn't really make any difference because the packages are already very far away. So they won't be interacting. The interaction can be neglected. So whether the v is there or not, it doesn't really change much. In the plane wave picture, well, there's all these problems with plane waves. Again, it doesn't change the result. So at t equal to minus infinity, there are no interactions. The interactions become significant for times of the order of 1 over eta, or minus 1 over eta. So since eta is very small, so interactions become significant at a very early time. And then at t equal to 0, it's at its maximum value. And keep in mind that eventually I should take the limit eta goes to 0. So psi of t in the interaction picture will be psi of, let me just write psi 0. And in fact, I will take psi, my initial state, to be some plane wave. No, let me keep it psi 0. I can take one particle, two particle, I mean, it can be arbitrary number of particles. Minus I from t0 to t, vi of t prime dt prime, psi 0, plus the other terms. Let me avoid writing them for the time being. And what I will be interested in, well, let me even call this psi I. The initial state. What I'm interested in is this one. This is what I would like to calculate. Well, eventually the probability, well, what will be the probability that my particle will be in this psi final state? Let me call it this one. Well, this will be equal to my final state, my initial state evolved over time e to power minus I h of t minus, let me put the t0 here. This is what my probability will be. This I can write as t minus t0, which will be equal to minus I e f t minus t0 f, the evolution operator in the Schrödinger picture. You see, the amplitude in the Schrödinger picture and the amplitude in interaction picture, they are not equal to each other. You see, there is that phase. But if the final state is also an energy eigenstate of H0, that is what I use over here, that is just an overall phase. When I take the absolute values, well, it won't change anything. Which in my case is now so if I am interested in probabilities, I can do the same thing in the interaction picture, as long as I stick with eigenstates of H0. The probabilities will be the same whether I calculate them in Schrödinger picture or the interaction picture. They will be the same. The probabilities, not the amplitudes. The amplitudes will differ by a phase. An infinite phase, but a phase, so the absolute value is just 1. Now, I will take the initial and the final state to be different. So the first term in this expansion, this is 0. I need to calculate this one over here. Let me just look at the time dependence first. Remember, the operators in the interaction picture evolve by H0. So this is e to power I h0 t prime v e to power minus I h0 t e to power eta t. That eta eventually I will set to 0, t prime, which is e to power I e final minus e initial minus I eta t prime vfi. So this is that matrix element. So this is equal to minus I, the first term is 0. I'm assuming the initial and final states are different. That's why I assume it to be 0. From minus infinity to t dt prime e to power I e f minus e I minus I eta t prime vfi. Well, you see that eta term makes sure that my exponent goes to 0 at t is equal to minus infinity. So I can easily take that. I can, without any problem, evaluate this integral. And that integral is minus I e to power I final minus e initial minus I eta t minus 1 divided by I e final minus e initial minus I eta. So these will also cancel. Let me take out this factor. What will remain is just 2I sine of I eta. Well, what is the transition probability? What is the probability that at the time t I will observe my particle in this state? F, just the absolute square of this 4 sine squared. Yeah, there's over 2. T divided by squared. Now let me take the limit as eta. Let me set eta to 0 at this stage. Where omega is E final minus E initial over h bar if we weren't using h bar is equal to 1 unit. Now, what does this function look like?
It looks like if I light an atom so that there's a transition property for the electrons from up to upright.
Let's plot it as a function of omega. Well, when omega is equal to 0, in the limit omega goes to 0, it will just go to t squared. This is t squared because sine of x over x goes to 1 as x goes to 0. Then it will be also, it will have this oscillating behavior. There's this 1 over m squared term. That is why the amplitude will diminish as 1 over omega squared, or 4 over omega squared. But this will be the behavior. Now, that point is at omega is equal to 2 pi over t. No, pi over t. That is when omega t over 2 is equal to pi, 2 pi over t. So, you see, there's that large peak. That large peak extends up to 2 pi over t. And remember, t is very large. So that peak is very narrow and very high. So it's almost like a Dirac delta. You see, omega is, in a sense, the violation in energy. EF minus EI. So you see here, delta, if you call this length delta E, that width, delta E times delta T, which is just, let's say, T, is somewhat around 2 pi. If this condition is satisfied, then the amplitude is large, can be large. If this condition is not satisfied, then the amplitude will be negligible. So this is the energy-time uncertainty relation that we have. So what is the limit of CFI as t goes to infinity? Remember, eventually we will be taking the limit t goes to infinity. Well, there are a couple of ways you can approach this problem. One is, okay, we already kind of know that it has to be some kind of a Dirac delta. Dirac delta of omega over 2. So we can say that for very large t, for omega much larger than, well, t much larger than 1 over omega, CFI should be some normalization times the Dirac delta, omega. This is what we expect. But if this is true, then integral of CFI over omega, by the way, omega can be also negative. Final EF can be less than EI. There is nothing that prevents that. The integral of CFI from minus infinity to infinity should be equal to n. If in that limit, okay, at least first of all, we know that for very large t, CFI is 0 unless omega is 0. That is basically what it tells me, that it's probably something related to the Dirac delta function. If it is the Dirac delta function, this condition should satisfy whatever the value of t is, as long as it's very large. Well, let's see. From minus infinity to infinity d omega, CFI is sine squared omega t over 2 divided by omega over 2 squared. Let me just make a change of variable. X is equal to omega t over 2. X, my integration variable, not the position. Or, well, let me change. U is omega t over 2. So omega is 2u over t. So that integral becomes 2 over t minus infinity to infinity du. This is my u integral. Sine squared u divided by omega over 2 is u over t squared. So this is 2t times minus infinity to infinity du sine squared u over u squared. And keep in mind that although it looks as if at u is equal to 0, it seems to have a divergence. The limit is finite. The limit of sine squared u over u squared as u goes to 0 is 1. So this is a regular integral over minus infinity to infinity. which you can evaluate using, I don't know, complex integration. At least this much tells me that CFI, when t is very large, has to be some number. By the way, it turns out that that coefficient is proportional to t. Now that's kind of problematic, but we will interpret it in a moment. It should be some constant times the Dirac delta function, because this is just a number. Furthermore, this integral is independent of the value of t. So that integral is also valid when t goes to infinity also. This is one way, yes?
It does not satisfy the modeling of the function to a Dirac delta doesn't make any sense to me. It's an undamped sinusoidal wave, then I can model every undamped sinusoidal wave to a Dirac delta.
No, it's not a sinusoidal wave, that's the issue. You see, this function is, for t very large, has this shape.
But does it? How much the amplitude did change between two top points of the?
You mean this top point?
Yeah.
This is t squared.
This is one, right?
That is t squared.
That is CFI. That axis is CFI, right?
You see, look at this one. This is sine squared omega t over 2 divided by omega t over 2 squared times t squared.
Right. Still, t is 0 there. No.
No, t is, I'm taking the limit t goes to infinity. Omega is 0 at that point. The horizontal axis is omega.
But still, omega will be 0 for every time smaller than the interaction time.
No, t is independent. I'm taking t goes to infinity. T will be very, very large. But in that limit, this function is 0 unless omega is very, very close to 0. I'm not restricting my t. I'm taking t go to infinity eventually.
Before any interaction with the potential, the omega will be 0, right? There won't be any scattering, so the E
No.
particle won't change.
No, you see, look at what I'm calculating here. I'm calculating the amplitude that I have a particle with in the initial state I at t is equal to minus infinity, and at t very large, I'm looking at the amplitude that it will be in the final state psi f. Psi f is at a very large time. It scatters somewhere in between these two times. I don't know when, but at some time. And what it turns out is that if you just look at it at a finite time, I mean, you have an initial state at, I don't know, 10 to the power minus 9 seconds. Afterwards, if you measure the energy, you might have energy violation. But if you look at, if you create your state and wait for a very long time, you don't have any energy violation. Energy has to be conserved, that is, omega has to be 0. This is essentially what this function tells me.
I encounter my potential, I jump to a state.
Is
then
it?
I continue at that state. I got the energy from the potential, I interacted with the potential, I got the energy still conserving the system.
No. No. You see, remember our first discussion. Probably you were not here. These states, EI and EF, they are not energy eigenstates of my Hamiltonian.
But at infinity, I'm a free particle.
They are energy eigenstates. They're not energy eigenstates, meaning that their energy, if you measure their energy, you will get different values. At infinities, they approximate energy eigenvalues. So only at infinities I can talk about them being actually energy eigenstates, not right at the moment of the interaction, because they're not energy eigenstates. They can have any energy of the full system.
But the thing I'm calculating, isn't it the initial state at minus infinity and the final state at the plus infinity? So I am in the energy eigenstates, and I am measuring how much my energy changed during this jump in the interaction?
When does it happen?
At some time, I don't know, call t.
And it can
t
have,
equals 0.
that's the crucial point. It happens anytime.
Right, but I'm at the infinities.
So,
So minus plus infinity, minus infinity.
Okay.
something.
exactly. So you see, you are, from what I understand, you say, I have my particle, it scatters at some time with my potential. That is where the mistake is. I don't know. There's all the uncertainty in time. I don't know when it scatters.
But the
And-
function is
Uh-huh.
on the whole domain, isn't it?
No. Yes and no. You see, that is why I mentioned the wave packet description. In the wave packet description, okay, there is this localized packet, so it's not all domain, it's not overall space, but it gives the same answer.
Isn't the energy change due to potential of the Hamiltonian, the interaction? So, our change in the energy, should our change in the energy correspond to violation of energy conservation? Because there is this potential and I can borrow energy from there.
No.
Isn't that the question?
You see, let's look at the same problem from classical physics. We know that the energy is conserved. Right? There's energy conservation. Let's assume that energy is somewhat localized over here in this region. So I send a particle. So I say this is my region where V is non-zero. I send my particle. I don't know what the potential is. I don't even need that. Well, it will come here. It will interact with the potential. Inside the potential, I don't really know what the energy of the the total energy will still be the same. The total energy will be whatever the initial kinetic energy the particle has. But the kinetic energy of the particle, let's stick with that, I don't know what that is, if I don't know the exact form of the potential or the exact position. And eventually my particle will come out with some energy. And the final energy of my particle should be the same as the initial energy of my particle because energy is conserved. Because energy conservation is independent of whether you have a potential or not. Even if you have a potential, we talk about potential only if the total energy is conserved. As long as there's no time dependence in the potential, which we introduced, by the way, as long as there's no time dependence in the potential, your total energy will be conserved. And if you are looking at regions very far away, the only energy the particle has is whatever kinetic energy it has. This is what happens in classical physics. This is also what should happen in quantum physics. But what happens in quantum physics is a bit more complicated because when we look at the scattering amplitude, this amplitude between two initial and the final state, even if their energies are different, well, the amplitude is non-zero. So there's no energy conservation. It seems that there is no energy conservation in quantum mechanics. But the thing is, what we should compare. We should compare this picture where we know the initial energy at a faraway distance and the final energy at a faraway distance. We should look at this amplitude. And what this function tells me, you see, remember, I'm making the measurement at the time t. If t is large enough, well, I have this potential, everything, all the wild things might happen in the region of the potential. But if I go out of the potential in a region far away from the potential, that is for large t, if t is large enough, then this function is nothing but the Dirac delta function, which tells me that the probability is zero unless energy is conserved. This is what this function tells me. In the region of the potential, these states don't have even an energy. So it doesn't really make too much sense of talking about their energy in the region of the potential. Whether they gain energy or give out energy, they're not energy eigenstates. I can talk about energy if I'm very far away, sufficiently far away, the energy of these free particles. And in that limit, I have energy conservation. Now, this was one derivation of the limit of very large T. Yeah, this kind of, yeah, it's nice if you understand it. It gives you more intuition in these problems. Well, there's another mathematical derivation, let's say. I'm calculating the square of this thing. Which is from minus infinity to t, dt prime e to power I omega minus I eta t prime. I will set eta go to 0. T is very large. So let me just replace t by infinity in one of them. Then, of course, you will complain, why not replace it in both of them? Give me a moment. Let me just replace it by infinity in one of them. What happens the second, that integral becomes a Dirac delta function. Well, whatever multiplies that Dirac delta function, I can just replace omega by 0 in that function. If I do that in the second integral, it becomes from, let's say, minus infinity to t dt prime, which is 2 pi Dirac delta omega t plus some constant. I'm not writing that is infinite. I don't like it. You see, we have energy conservation due to that Dirac delta omega. We have again this linear T dependence. Well, that is not so nice because you see we are doing a perturbative expansion. The first term was 0, the second term is non-zero, but if T is very large, I mean, this is a very large probability. Probability has to be less than 1. So this is kind of, but what are we actually interested in? The probability or the probability rate? Because eventually we will be calculating the scattering cross-section, which we define in terms of the number of particles reaching my detector per second. I'm actually interested in the rate of the scattering. So d by dt is constant. Yeah, my potential is constant. I'm constantly sending waves. The transition rate, I was expecting it to be a constant, and it is constant.
You didn't justify why not swap both T for infinity?
Because I know the answer.
Yeah.
Well, if you, well, okay, if you want to be formally more correct, what I'm interested in is this derivative. Which is twice this is what I'm interested in. Now, this first one, if T is large enough, it's a Dirac delta. Well, this is just 4 pi Dirac delta omega. Dirac delta omega, so this is 0. So this whole thing is 1.
You're getting a factor of 2 though. That's
Yeah, that's what I was thinking now. Let me check. I mean, now the factor 2 seems to be more correct. Because probably I have to do either this one is very large, keep that one small, this second one is large, keep the first one small, and then there will be some corrections.
If you,
Hmm?
if you put, for example, instead of TV, if you put time goes to infinity, the time, when you take limit, there must be 2t. So it is 4 pi Dirac delta.
Where?
Upper part.
Here.
2pi Dirac delta integral içerisinde eksi infinity'den t'ye kadar gidiyor ya.
Hı hı.
Biz diyelim ki limit t'yi sonsuza götürdük. Alttaki minus infinity'yi de eksi t biçimde yazdığımızda 4 pi kısmı gelir.
I don't like that.
Okay.
Anyway, so I agree. There's the issue of the 2 over there, and probably this seems to be the more correct answer, to be honest. Let me check that, and probably not today, but on Monday we will discuss it.
Zihnimin çok derinliğinde bir yerde 2pt geliyor diye kalmış bu arada. Yani 2pt daha doğru geliyor ama.
Zamanı minus infinity'den başlatma sebebimiz ne?
Very early time.
Ha. Yani zero
I
olarak-
mean,
Ha.
I could have kept it as minus capital T, or T0. But eventually I will be taking all these limits as initial and final time goes to 0, goes to infinities.
Başlangıcı eksi infinity aldığımız zaman bizim t'yi nereye koyduğumuz, yani orijini nereye koyduğumuz arbitrary kalmıyor mu?
Sure.
Ben her zaman shift edip t'yi sıfıra set edebilirim ya da o zaman da ya da bütün t'ler artı sonsuz gibi kalabilir. Ya burada çizdiğimiz t'yi bir parametre olarak alıp omega ve CFI grafiğimiz bizim şeklinin ne olacağı bizim t'yi de seçeceğimizle alakalı kalıyor.
Sure, but the derivative will not depend on it.
Yeah. That's correct.
You see, this is actually the term that I didn't write over here. Let's say that is minus t. Well, this is t plus capital T. But when I take the derivative, that shift in a sense doesn't really change anything. So let's give a 10-minute break and we will continue after the break.